Today we're going to close out derivatives by talking about related rates. So this brings together all of the pure math rules that we learned through the chapter, and we're applying them in context. And unlike before where we just had arbitrary x's and y's, these derivatives actually mean something in context. And the best way to show this is with an example. Here I have the equation p times v equals nRt, where p, v, and t are functions of time, and n and r are constants. And if you have chemistry background, you'll recognize this as the ideal gas law. And using this equation, we're asked to find dp dt. This just stands for the derivative of p with respect to t, and t here stands for time. If I want to get a dp dt out of this equation, what we're going to do is we're going to differentiate both sides with respect to t, like so. And by the way, we always differentiate with respect to time in a related rates problem, since the definition of a rate is a change in quantity over a change in time. Let's work the right side first. So here we're told that n and r are actually constants, so we can pull them out of the derivative, like so. Now we have to find the derivative with respect to time of big T. But if you look over here, we're just told that t is a function of time, but we're not actually given what t is. If you'll remember, this is really similar to implicit differentiation, where we didn't know what y was, so we just left the derivative of y with respect to x as dy dx. And that's exactly what we're going to do here. We don't actually know what this t function is, so we're just going to say the derivative of t with respect to t is d big T over dt. And now I'm going to substitute this back into here. Now we're going to work out the left side. If you look up here, we're told that p and v are both functions of time. So this is actually two functions being multiplied by each other. So to differentiate this, we have to use the product rule. If you remember, the product rule is first d second plus second d first. So our first is p, and our d second is the derivative of v with respect to t. But again, just like this big T, we don't actually know what the function v is. So the only way to express the derivative of v with respect to t is dv dt. Now we have plus our second function times the derivative of the first function with respect to t, or dp dt. Since again, we don't know what the p function is, so this is the only way to express its derivative. Now I'm going to take this and substitute it back up here. Now I'm left with this equation, and remember, we are asked to find dp dt, so I'm going to start by moving this to the left, like so, and finally I'm going to divide both sides by v, like so, and without any given numbers, this is our expression for dp dt. The reason why this is called related rates is because we're literally relating different rates in this equation. We're saying that the rate of change of p is equal to 1 over v times nr times the rate of change of t minus p times the rate of change of v. And again, the way we do this is we differentiate our given equation with respect to time, and then we algebraically solve for what we're asked for. But sometimes you might have to create and differentiate your own equation. Like this one. At first, it seems like we're given almost no information that we need to solve it. But there actually is a pretty clever solution to the problem. Take a second to attempt this yourself and then check your answer. After recording the video, I realized that the problem I just gave you is actually impossible because I didn't give you dy dt. So you should just try and solve it symbolically. And I think I subconsciously realized that while I was solving the problem because my answer is symbolic too. First, let's begin by finding this missing height of the ladder above the floor. And the way we do this is realizing that the ladder makes a right triangle with the wall and floor. Because it's a right triangle, we're going to use the Pythagorean theorem to find the side. We start with a squared plus b squared equals c squared, then we substitute our values, and then we algebraically solve for b, and we find that this is 8 meters above the floor. We found the length of the missing side, but we still need to make an equation to relate some rates that are in this problem. What if instead of these specific numbers, we generally refer to the sides as x, y, and z? Then when we apply the Pythagorean theorem again, we see that x squared plus y squared equals z squared. This is because as long as the ladder keeps contact with the floor and the wall, this always maintains a right triangle. And this is the equation that we're going to use to relate the rates in our problem. And if we look at our diagram here, this arrow represents the rate at which x is changing, or the change in x over the change in time. And similarly, this represents the change in y over the change in time. We're going to bring these rates into our equation by differentiating it with respect to time, like so. And this is the equation we get after we implicitly differentiate. From here, you might immediately be tempted to just do the algebra and isolate dx dt, but we can do a little more simplification. This is where the context of the problem comes back in. On the right, we have 2z times dz dt, or the rate at which z is changing. But if you look here, as the ladder slides down the wall, the length of the ladder, or z, doesn't actually change, so dz dt is 0. This simplifies the entire right side to just 0, and now we can do the algebra. Here I moved 2y dy dt to the right, and the 2's cancel, giving that dx dt is negative y over x times dy dt. This negative in front might be confusing at first because we know that the ladder is moving to the right, so dx dt should be positive, right? In reality, it actually is because of dy dt. If you look over here, as the ladder moves to the right, it also moves down, making dy dt negative. This actually cancels the negative here, keeping dx dt overall positive. And another related rate scenario that you'll commonly encounter is when a container is leaking water. So we have a cone leaking water at a constant rate of 3 liters per second. What that means is the volume of the water is decreasing by 3 liters per second, or dv dt is negative 3. Then we're told at some instant the height of the water is 2 meters and decreasing by 0.25 meters per second. So what that tells us is h equals 2 and dh dt is negative 0.25 at this instant. Finally, we're told that the radius of the water is half a meter, or r equals 1/2. We have to find how fast the radius of the water is changing, or dr dt. So first we need to find an equation that relates all of these quantities, and the equation that we're going to use is the equation for the volume of a cone, like so. And we're going to differentiate this with respect to time, like so. We have to find the derivative with respect to time of v. Well, we don't actually know what the v function is, so we're going to leave it as dv dt. On the right side, I can simplify a little bit because pi over 3 is a constant, so I can pull that out of the derivative. And from here, we have to use the product rule to differentiate r squared times h, like so. So I have first the second plus second, and all of this is the first because of the chain rule. Now we just have this, and it's a matter of algebra to isolate dr dt. First, I'm going to begin by multiplying 3 over pi to both sides, like so. And then I'm going to subtract r squared dh dt from both sides, like so. And finally, here I'm going to divide by 2rh. And this is our expression for dr dt, and now we just have to plug in the numerical values we established at the start of the problem, like so, which reduces to this, and this is our numerical answer. That's how you solve related rates problems.